Somewhere in the constellation sextants, hidden inside a patch of sky no wider than the width of your thumb held at arm's length. To understand why this matters, you have to understand what astronomers expected to find when they built the James Webb Space Telescope in the first place. For decades, our picture of the early universe rested on a well-tested framework, often called the standard cosmological model. In that model, the first few hundred million years after the Big Bang were supposed to be a quiet, chaotic nursery. Small, faint, irregular clumps of gas slowly collapsing under gravity, gradually forming the first tiny protogalaxies, dim and simple, built almost entirely from hydrogen and helium because nothing else had been forged yet. Heavier elements, carbon, nitrogen, oxygen, the atoms that make up planets and people were expected to be essentially absent this early, since it takes generations of stars living and dying to manufacture them and scatter them into the surrounding gas. According to the model, the universe simply hadn't had enough time to build anything complicated yet. That model wasn't a guess. It was built from decades of careful theoretical work, tested and refined against every observation available before Webb existed. Ground telescopes and even Hubble simply couldn't see far enough back to check it directly. Light from an object this distant is stretched by the expansion of the universe into wavelengths far beyond what the human eye or a visible light camera can register, drifting deep into the infrared. To actually test whether the earliest galaxies looked the way the model predicted, you needed an instrument built specifically to catch that faint, stretched ancient light. That instrument is Webb, sitting nearly 1 million miles from Earth, cooled to within a few degrees of absolute zero so its own heat doesn't drown out the whisper it's trying to hear. Webb was designed to test that model directly, by looking further back in time than any telescope before it. And almost from the moment it turned on, it started finding galaxies that didn't fit the story. Bright, compact, oddly mature-looking systems. Appearing at distances the models said should only contain faint, half-formed wisps of gas. Astronomers initially treated each one as an outlier, a strange exception worth investigating individually. Then, the exceptions kept coming, and in 2025 one of them became impossible to file away as a fluke. On May 16, 2025, a team of astrophysicists led by Rohan Naidu at the Massachusetts Institute of Technology was combing through Webb's NIRCam images of the Cosmos Legacy Field, a mosaic of the sky roughly 10 times the angular area of the full moon, when they flagged a single faint point of light that didn't match anything nearby. Follow-up observations with Webb's NIR spectrograph confirmed what the imaging had only hinted at. The object, now named MOEM Z14, had a redshift of 1444, the highest ever confirmed for any galaxy. In plain terms, its light has been traveling toward us for roughly 13.53 billion years, meaning we are seeing MOEM Z14 exactly as it looked just 280 million years after the Big Bang, when the entire universe was 2% of its current age. That alone would have made headlines, a new record for the most distant galaxy ever observed, another line added to an already impressive list. But the record wasn't the disturbing part. The disturbing part was what the galaxy contained. MOEM Z14 is bright. Unusually, almost uncomfortably bright for something this early and this small, only a few hundred light years across according to the team's measurements. And when researchers broke down its spectrum, they found something that, according to current models, should not have had time to exist yet. Clear signatures of carbon and nitrogen, heavier elements that can only be produced inside stars, and then released back into space when those stars die. For those elements to already be present in meaningful quantities at 280 million years after the Big Bang means an earlier generation of massive stars had to have formed, burned through their fuel, and exploded, all before this galaxy's light left on its 13.5 billion year journey to reach us. The math is uncomfortable. There simply isn't supposed to be enough time in the timeline for that entire cycle to have already happened. Some researchers studying the object have gone further, proposing that MOEM Z14 may host something even stranger at its core, an actively accreting black hole far more massive than anything current models predict should be able to form this early. If that interpretation holds, it would mean the black hole seeds that eventually grow into the supermassive giants sitting at the centers of galaxies, like our own Milky Way, either formed through some exceptional, still unexplained mechanism, or existed in a primordial form dating back to the earliest moments of the universe itself, long before the first stars had even finished assembling. And here is the part that turned this from a strange one-off into a genuine crisis for the field. MOEM Z14 isn't alone. The same survey that found it, a project researchers nicknamed Mirage or Miracle, was specifically designed to hunt for other bright objects at similarly extreme redshifts across roughly 350 square arc minutes of sky. What they found is that galaxies this luminous, this early, are not rare exceptions. According to the published analysis, the number of these bright, ultra-distant sources is over 100 times higher than the standard pre-Webb consensus models predicted. Not twice as many, not 10 times as many, over 100 times more than the math said should be there. That single number is why astronomers aren't just filing MOEM Z14 away as an interesting curiosity. A single unusual galaxy can be an exception. A population of them, appearing in numbers 2 orders of magnitude beyond what the models allow, is a sign that something structural in our understanding of the early universe is incomplete. As one of the researchers involved put it in the team's published statement, Webb appears to be pushing the cosmic frontier further and faster than anyone anticipated, bringing the era of the very first stars into view sooner than expected. So what actually breaks? That's the question dividing cosmologists right now, and there is no single agreed upon answer. One camp argues the fix lies in star formation itself, that the earliest galaxies were somehow able to convert gas into stars with far greater efficiency than current simulations allow, producing bursts of light bright enough to explain what Webb is seeing without needing to touch the underlying cosmology at all. Another camp points toward those unexpectedly massive black holes, arguing that if accreting black holes are contributing significant light to these early galaxies, the apparent brightness problem could be explained without demanding an implausibly fast star formation history. A third, smaller but increasingly vocal, group argues that the discrepancy runs deeper still, that explaining what Webb is finding may require adjustments to the cosmological constant, or to how we model the influence of dark energy on the earliest phases of cosmic history. None of these explanations currently commands full consensus. All of them are being actively tested against new data as it comes in. It's worth being precise here, because headlines chasing clicks love to claim physics has been broken, and that framing oversells what's actually happening. Nobody studying MOEM Z14 believes the fundamental laws of physics, gravity, thermodynamics, the behavior of light itself have been violated. What's being challenged is something narrower and, in its own way, more interesting. The specific timeline and mechanisms by which the standard model says galaxies, stars, and black holes are supposed to assemble in the universe's first few 100 million years. That timeline was built from decades of careful theoretical work and observations from telescopes that simply couldn't see this far back before Webb existed. Now that we finally can see this far back, the universe is turning out to be more mature, more chemically developed, and more structurally complex at these early epochs than that timeline ever predicted. Whether that means the standard model needs a modest correction or a genuinely deep rethink is precisely the question the next several years of research are going to be spent answering. And that distinction matters more than it might seem. Science doesn't advance by declaring the rulebook shattered every time a surprising object turns up in the data. It advances by treating each surprise as a measurement to be checked, modeled, and either absorbed into the existing framework or used to rebuild it from the ground up. What makes MOEM Z14 different from an ordinary anomaly is the scale of the correction now on the table. A single unusual object might demand a footnote. A population of objects appearing 100 times more often than predicted demands astronomers go back and question assumptions baked so deep into the standard model that nobody thought to test them directly, simply because no instrument before Webb had ever been able to. What makes this moment different from earlier rounds of early galaxy surprises is the sheer weight of evidence now stacking up behind it. MOEM Z14 replaced a previous record holder, a galaxy called JD's GS Z13 at a redshift of 14.8 Need, itself once considered a startling outlier. Now that record has already been broken again, and the survey behind MOEM Z14's discovery suggests dozens more objects like it are likely waiting to be confirmed across the sky. Each one adds another data point to a pattern that keeps pointing the same direction. Whatever process built the first generation of galaxies, it worked faster, more efficiently, and on a larger scale than anyone modeling the early universe had accounted for. The next chapter of this story is already being written. Follow-up spectroscopy on MOEM Z13 and its neighbors is ongoing, aimed at pinning down exactly how much of its light comes from stars versus a possible central black hole, and exactly how enriched its chemistry really is. Meanwhile, NASA's Nancy Grace Roman Space Telescope, targeted for launch in 2027, is being built specifically to survey much wider patches of sky than Webb can manage alone, hunting for more of these extreme early objects, so Webb can then follow up with the kind of detailed spectroscopy that turned MOEM Z14 from a strange smudge into a confirmed record. Between the two missions, astronomers expect the population of impossibly early, and with it, the pressure on the standard model to explain how the universe managed to grow up this fast. For now, MOEM Z14 sits in the data as both a triumph and a warning. A triumph because it proves Webb can see further into the past than any instrument in history. all the way, back to a universe barely 300 million years old. And a warning, because everything Webb finds out there in the deepest, oldest light in the observable universe keeps saying the same uncomfortable thing. The story we've been telling about how galaxies are born may only be a rough draft. The universe apparently grew up faster than the textbook allowed, built structure and chemistry ahead of schedule, and left the evidence sitting in the sky for over 13 billion years, waiting for an instrument sensitive enough to finally read it. No one knows yet how many more chapters of that rough draft are still sitting out there in the dark, unread, at redshifts even Webb hasn't reached. If you want to be here, as astronomers work out whether the standard model bends or genuinely breaks under the weight of what Webb keeps finding, subscribe and turn on notifications. Because the deeper this telescope looks, the stranger the early universe keeps turning out to be, and the next record it breaks might be the one that finally forces cosmology to rewrite its own opening chapter.